Welcome to the 2025 AMSI Summer School Public Lecture. My name is Hao Tian Wu. I'm a senior lecturer in the School of Mathematics and Statistics at Sydney Uni. I'm also a co-director of the AMSI Summer School this year. First, we acknowledge the traditional owners of the land on which the University of Sydney campus stands, the Gadigal people of the Eora Nation. We pay our respects to those who have cared and continue to care for country. I want to say a few words about this AMSI Summer School, which is an annual national event for honors and postgraduate students, early career researchers, and industry professionals from all over Australia as well as overseas. This year, we have the 23rd Summer School held for the third time on Sydney Uni campus, and the summer school features a variety of subjects given by the experts, also networking and careers opportunities, as well as public outreach event, which is the lecture this evening. I was hoping to see some young faces. I think I still see some young faces. So I hope you will take this summer school in the future, yeah? Yeah, you can repeat, even if you are taking it now. And next, the public lecture this evening, as you can see with this banner, is generously sponsored by the Sydney Mathematical Research Institute, i.e. SIMRI. We thank SIMRI's generous support as well as the meticulous organization for this event. Okay, so now it's my great pleasure to introduce the speaker this evening, Dr. Jordan Pitt. Dr. Pitt is a lecturer in the School of Math and Stats at Sydney Uni. He's also Associate Dean, Indigenous Strategy and Services at our university. Dr. Jordan Pitt is a descendant of the Birri Gubba people and an applied mathematician. He completed his undergrad and a PhD at ANU, working on numerical methods for tsunami modeling. And he now studies the interaction of ocean waves and sea ice to improve climate models. And this is a continuation of the work he started when he was a postdoc at the University of Adelaide. Yeah? And in addition to his academic time, he also has worked at Geoscience Australia and the Australian Taxation Office on projects from modeling tsunamis to phone call times. So without further ado, let's welcome Jordan Pitt to tell us about his journey, his mathematical journey from play to sea. Yeah, let's welcome.
Thanks, Haoshan. I also wanted to additionally say Niani, Nalawanguan, Mari, Bujari, Gadinurada, sorry. And that just means welcome to Gadi country in the language of the Gadi people. And of course, for those who don't know, the Gadi refers to the grass tree. Here we can see on campus some examples of it, although of course it was even more prominent before the campus was here. So my journey from play to sea, I'm gonna just go first with a bit of prologue, my motivation for the talk, why it's this way, please forgive me. And then we'll head into the beginning. Really, my journey kind of starts with mathematics as process, kind of learned that through primary school, and which is that picture there of me. Yeah. And then through the middle, where I actually engaged with maths much more deeply and had mathematics really as play, and I guess profound play as well, as we'll see. And I did attend AMSI back in 2016, so 9 years ago. Maybe I'll do it again, I don't know. Haoshan was really selling me on that one. And then finally, we will go to the sea, where I'm looking at the interaction of ocean waves and sea ice, as Haoshan said. Okay, so my prologue, motivation. So I kind of gone through all this academic training, giving academic presentations, and I'd always considered that a good presentation, and you have to show an equation for mathematicians, otherwise, unlike non-mathematicians, they will turn off if you don't show an equation, as I've actually learned the hard way. So yes, I thought a good presentation was, we're gonna use sums in this case, is a clear structure, plus some nice concise explanations, some nice figures, and then of course practice, and more practice. And of course you can reduce this equation to 3 times practice, as we saw there. And yeah, I'd done that a bunch of times, And then I gave an outreach talk last year, and I realized, I was kind of missing something in my talk, and I felt like I wasn't kind of bringing my full self to it. And I guess, I kind of learned, a bit of a robotic style, so hopefully it's a bit different for this lecture, so please bear with me on that. For me, it's a bit of fun, silliness, and we'll see that. I don't promise it to be a laugh fest, but we'll have a bit of fun with it. Yeah, so that's the talk, the motivation, why you have to forgive me later. So a couple of warnings for my mathematical journey in the story. Stories, very easy to construct in hindsight, of course. And I'm reflecting especially, for some of our students, some of the AMSI students, it's a bit of a mess of a maze in front of you. You can go in a lot of different directions, but it'll all make sense in the end, looking back, actually. But as Haoshen mentioned, I'm going to kind of omit from this talk my time at Geoscience Australia, ATO, and modelling and studying tsunamis, although I'm, of course, happy to answer any questions you might have about those. And then the second point, an important one, especially for the AMSI students, I guess, I did not get here by optimizing my career. And I know with the fancy title that Haoshen mentioned, it might seem like I did, but to actually drive this point home, I have a bit of a personal story, and I wanted to highlight this as well because I don't think we talk enough about our personal sides of our journeys through our careers as well. So I was in 2018, I was in New Zealand for a trip with a colleague, attending a conference. So that was very cool. I got some money to go, felt awesome. I'm at the top of my career, that's what it felt like. And then out of the blue, I get a friend request from someone I hadn't spoken to in a long time. It didn't take, although it's someone I really wanted to reconnect with, and it didn't take very long at all for us to be, long distance in 2018 for the whole year, basically. And there she is on the left. And you can tell this is evidence that we're long distance because no one else takes selfies in airports, okay? The only two people doing that is long distance relationships. And I decided that I would submit my thesis in 2019 and move to Brisbane. And I didn't have a job lined up at UQ, Griffith, QUT, had no idea really. I'd just move up there and see how it went. And last year I got married, so that worked out well. And of course, thank you. Yeah, okay, yes. There she is there at the front row. Yeah. Loves getting attention, by the way. So my point is, you don't have to get married. That's not what I'm saying. But what I am saying is, especially for our AMSI students, I think it's important to sell that you really should have, some kind of fulfillment and personal growth outside of your career. And I found that I think I wouldn't be here today without the personal growth that I've had along this journey, kind of toughing it out in Brisbane. That's why I worked at the ATO, by the way. I don't think I'd be in an associate dean role, for instance, without this having happened. So very grateful. And you talk to every mathematician that I've talked to, like the president of the International Mathematics Union, which is a big fancy international organization, and he has personal reasons for why he went to the universities that he did as well. So across the board, and I wanted to highlight that today. So that's the personal warnings prologue part over. Now to the mathematical journey. Okay, so maths in primary school, I said it was process, no play. So my mathematical memories are really things like worksheets. This one, double the number and get the right answer and get lots of ticks and get a big score at the end. And that was fun, I guess. Carrying the one, that's what I remember very distinctly for our addition. And also subtraction, I guess, that kind of funny unit stuff. And then finally, multiplication. It's a multiplication table. And this was burned into my mind. And you can buy it for $17 on Amazon. I don't have an affiliate code, but they do ship it within a week, so feel free. That's that one, by the way. And I did love it. I'm not going to admit that I didn't. But I think what I liked about it was that I found it relatively easy, a fairly good memory. It's good at memorizing things, and someone told me I was good at maths because I got a high score in it. So yeah, woo, I did it. I'm a mathematician. And that was all kind of, the bottom fell out one day, I guess, when in year 6, my teacher asked a very simple question, actually. What is multiplication? Yeah, and I looked within myself, and I guess the answer that came to me was kind of, well, it's a multiplication table. But that wasn't very satisfying, so of course I didn't say that out loud, even though, I'd kind of considered myself good at maths at this stage. And sure enough, I mean, there's no, well, at least the most kind way to say this, I guess, one of the, less gifted students, he was a friend of mine, it's okay, we hung out all the time, had the answer. And so that was a bit of a double whammy for me, it's multiple addition, 3 times 2 is 2 plus 2 plus 2. And I'd never actually, I mean, maybe I'd done that as a process, but I'd never actually thought about it any more than, that's a step to get outside of that multiplication table. And so I was completely dumbfounded. And of course, I put an equation for our mathematicians involved. So what do I do when I've had this earth-shattering revelation that I didn't actually understand what I was doing? I forgot about it. Yeah, who cares? And the teachers went right back to teaching me steps anyway, and I didn't actually have to engage any deeply. And I should probably say that this is not probably an indictment of the teacher, and more probably an indictment of my engagement with their classes, although, your mileage may vary on that one. But, I was a super cool kid, so actually I rode in on my skateboard, and I did a massive ollie, and then I rode away, forgetting about it, and heading into high school. And when I got there, I was a pretty good student. I would say I was like 70 to 80% in maths, but I was very firmly, I guess, in the middle stream when we started separating it out into multiple math streams. Cool, yeah. And then one day, we were learning about compound interest, and I put my hand up and said, didn't we learn this last year? And that's when I got put in the advanced stream. Okay. But, maths was still I'd learned this process before, so it was easy. But the advanced stream, it just seemed like more steps, but it was fine. I could just keep going with my maths as a process. I'll just follow the steps and keep going. I've learned this before. The only kind of real changes I experienced was, number one, I had a teacher that was actually passionate about mathematics and always tried to talk about how excited and enthusiastic he was to do maths. He would wax lyrical about drinking wine and solving maths crosswords. Yeah, I mean, I didn't really think that was cool, but I guess eventually maybe it did rub off on me, I guess, given where I'm standing today. But the next thing, and probably the more fundamental change, was that he started asking weird questions. So I remember one worksheet where he asked a bunch of questions that I hadn't really thought about before. So for instance, what's the square root of 0? And I could reason my way through this problem, but yeah, okay. It's a bit weird, I don't know, I hadn't seen the square root of 0 before, so I thought that was a bit funny. Worked that out. Of course it's 0. But then at the bottom, there was another weird question, even weirder. What's 1 divided by 0? I mean, I didn't know, and certainly no one had told me before, so it must be a bad question, of course. And I guessed, well, there's a 1 and there's a 0, 50-50 shot. I'm just going to say it's 0. I get an answer, yeah, and right off, do a kickflip over the whole class and get out of there. So the weird questions keep coming, and then one day I have a very vivid memory of this. We had a homework question which was, how many lines connect a number n points? And there's this extra stipulation on the end, which we'll kind of forget about, but is important for the construction, which is no 3 points lie on the same line. Well, obviously that worksheet was weird, but whatever. I mean, what a stupid question. I've dealt with lines and numbers, never lines and points, but never really thought about it. I mean, who even cares, really? And does it even have an answer? I don't know. So I went home on my skateboard, of course, and did a big jump. I think I did I can't remember another trick. I did a 360 and went home. Didn't bother answering it, of course. And then the next day I'm in class and the teacher's like, well, let's answer the maths question, of course, from the homework. Yeah, okay, whatever. And you have to keep in mind, this is year 9 maths, so he's not going to show a proof. he will just show a construction argument, but still, it was illuminating, although we'll see that I'm a bit skeptical. And what we're just going to keep in mind is number of points, number of lines, and we're just going to show his construction argument. So we're going to start with 1 point and then increase. So we have 1 point. Congratulations. So I have going to claim there's no lines because I don't have a point to draw it to. We can have a philosophical argument about that one, whatever. But what's more interesting is when we start adding those points and what happens. So I add my 1 point, and I can now draw 1 line. Wow. Yeah, okay, that wasn't too crazy. You know, I add a point, I can draw a line between the 2 points that I have. Okay, now I can add a 3rd point and get to that other solution. So that's when I have my 3rd point, and I can now draw 2 lines. Cool, I have a triangle. I've seen a triangle before. That's not too crazy, although you will probably start to see that pattern that's kind of emerging, right? So I can draw a line between every point that's already there, for instance. So when I go to my 4th point, I can now draw 3 lines to each of those previously existing points, in particular the top one, the bottom left, and the bottom right. And that gives me 3 points to add to my total, giving me 6 lines. 3 lines, I should say, before. So, great. Then he went to 5, and sure enough, this pattern's holding. I add a point, and I can draw precisely as many lines as there were previously existing points. And what this means is that the answer is that the number of lines you can connect to n points is the sum of all the numbers less than n. Yeah, cool. I mean, yeah, he did the easy problem. I mean, he did a few points. That doesn't hold. Where does that come from, you know? Surely it doesn't go on forever. So, you know, I'm very skeptical. I go home and I'm determined to keep the construction going. I start with my A4 sheet of paper, and I start with my 5 points that I've already shown how to draw to, and I get my 10 lines. Now I'm going to add a point, okay? Oh, wow, okay, so there is 5 lines, you know. Yeah, but maybe the next number will show something completely different. No, so I get up to 7, I get to 8, I get to 9, and we can see that pattern continuing. So when I add my 7th point, I can add 6 lines. When I add my 8th point, I can add 7 lines. And when I add my 9th point, I can add that 8 lines. And in this process, you know, I've expanded out to the full A4 sheet, and I've now had to start gluing all A4 sheets together with tape. I get to 21 points, which is 210 lines for those keeping score at home. And if you know the pattern for the sum, then that's going to be fairly obvious. And it's also a nice hint to check your answers, you know, if you want to go and fiddle around and figure out what the pattern is for a sum of all the numbers less than 1 to 20 in that case. Yeah, and I covered the whole table. So yeah, and it just kept working, and that's when it struck me, you know, that 21th point, I don't know what it was, but that's when, you know, covering the whole table, not only had I made like a nice picture, as you can see with all those triangles, but it also said something, you know, I'd realized something profound about the number of lines and points, and had a lot of fun. And this is, you know, going from that very dismissive, I don't know where that came from, by the way, very dismissive point of view, I don't have to answer this question, to, you know, covering a whole table in sheets of paper. You know, that was really revelatory for me. And so that's, you know, kind of my fork in the path. You know, I'm playing with maths now, and I'm enjoying it, and I'm engaged. So I really started to learn that, you know, maths is profound. It's saying something deep about objects that I had dealt with before, points and lines, but I'd never really thought about or didn't seem obvious at first. And it's also fun and it's beautiful at the same time. So, you know, all three. And I guess it's useful, and we'll see that later, but that was what really started me on my journey. As a consequence, of course, I was more engaged, and I thought about the steps and what they actually meant. So, you know, it really turned that multiplication problem around, and I was thinking beyond what the teacher was telling me and like, oh, what if I did this? What would happen? Or why can't I do it? And to give you an example that we've kind of seen before, I was writing my maths presentation, and, you know, I said that 3 times 2 is 2 plus 2. And then, of course, well, you could do the other sum. You could do 3 plus 3. And, you know, I mean, I can't give a convincing argument about why those two should be equal, except that they are. You can, of course, do very simple sums like this, but you can dig a bit deeper and figure out that they must actually be equal. And the way you do this is, well, I've solved out what multiplication is. It's multiple addition. And what's the addition of bigger numbers? Well, you just break it down into the ones that constitute those biggest numbers. So 2 plus 2 plus 2, well, 2 is 1 plus 1. So I can, of course, do 1 plus 1 plus 1 plus 1 plus 1 plus 1. Yeah. And I can do the same thing with 3. And actually, the brackets don't matter when I'm adding 1 plus 1. So both of these are just 6 ones added together. And then it's really foundational, and it must be the case that actually 3 times 2 is 2 plus 2 plus 2 and 3 plus 3 plus 3, because you've just kind of obscured that underlying structure of the ones, really. And this was all going through my head while I'm just writing this presentation, thinking about something else. And it's always good as a mathematician as well to go back and reanalyze some of those foundations, because you make a lot of assumptions and skips of intuition along the way, and sometimes you have to go test that. So I had a bit of fun with that, solving that problem for us today. Yeah, and of course, I'm more engaged. I'm actually doing maths a bit in the free time. So, and I guess fundamentally, as I kind of pointed out before, a bit of intellectual humility. And obviously it was something I desperately needed, because why was I dismissing questions? That was just bizarre. I really don't know where that came from. I think maybe, if I had to put it down to something, maybe being told I was good at the maths maybe made me feel like I was, king of the world in that sense. But, through kind of being beaten down, learned that intellectual humility. And something we desperately need to see more of in the world, but that's okay. Anyway, so speaking of that, I also had a lot of fun kind of escaping to maths as well. And it's something I reflected on, especially when I listened to a Quandamooka mathematician, Chris Matthews, talking about his journey with escaping the world through maths. And it's always been fun to play with rules and play around with that. But I think fundamentally what the biggest kind of escapism fantasy there was that we could play by rules that made a bit more sense than some of the rules that we see out in the world, especially, being Aboriginal. So yeah, it was a good time. And naturally I became a top student, and here I am. So I did manage to graduate with my PhD, and my maths teacher managed to attend. So that was a nice kind of closing the loop on that one. And the last point, I guess kind of a more general life advice thing, might not seem obvious given that I'm giving a public lecture, but I really did go from someone I would say not a whole lot of confidence, and I built a lot of confidence through my work and then through my social life as well. So, and now I have both, and they kind of go along parallel, but it was really important to me to kind of, that kind of building those skills and building that confidence that I probably didn't have as well. So getting good at something, aptitude as a tool to gain confidence. So yeah, here I am. Now we're talking about the ocean. Wow. So here is a ship heading down towards Antarctica, and we can see sea ice, which is those chunks of white floating on the ocean, which is the ocean surface is actually frozen because it's so cold, giving us this. And the ship is going through that sea ice cover. And because it's the ocean, we have waves as well. So what do? Well, I do the coolest job of all. I don't sit on the ship, no. I play with the whiteboard. I play on my computer, and I try and understand these interactions more deeply. And you definitely need both. Certainly appreciate, and I've worked with experimentalists and observationalists who are really good at their job, but likewise we need that mathematical insight to gain new perspectives, but also, I guess, fundamentally quantify some of those things that observationalists see out in the world, and what happens when you change one thing and what effect that actually has. You need a mathematical description of the problem to actually do that, whereas an observationalist can tell you exactly what happened on one particular day at one particular time. Okay, so sea ice, new kind of phenomenon. Well, it's the freezing, as I said, the freezing of the ocean surface due to those extremely cold temperatures we get around the Arctic and the Antarctic. And these, we can see, we have very blurry photo, but maybe it looks good from your view, hopefully. We have what are called pancake flows, and they're quite, they're called pancake flows because they're quite flat, and they have that kind of round shape with those raised edges, and that's caused by the freezing of the ocean's surface. And also those raised edges come from like that jostling between ice. And you get lots of complicated dynamic things going on in the sea ice cover, which makes it, of course, very interesting to model. But why do we care? Well, of course, you know, the big overarching thing that's going on, I don't know if anyone's aware, but the climate's changing. Hello. So sea ice has a big important role to play in the evolution of the climate. So in particular, sea ice drives ocean circulation and overturning. So I've got here a image of, a nice descriptive image of the ocean currents, and they're transporting heat and I guess salinity, as we'll see, around the ocean. And in particular, we have two branches. We have the red, warm surface water. Of course, it's warmer in the equator than towards the poles, but it's very warm compared to the water at the bottom of the ocean, which is in blue there. So how do we get from our surface to our bottom? Well, that all relies on the sea ice. So the sea ice, when you freeze the surface of the ocean, you're freezing the water. Seawater is salty, so you're actually rejecting the brine and getting very salty, dense water due to that salinity increase, and also due to the colder water as well. And when we get that denser water, it sinks to the bottom, and that's why we have these regions of the deep water formation, which we can see in the North Atlantic and in the Antarctic as well. All due to sea ice, and the reason why circulation of the ocean is important is because it regulates and moderates the temperature of the Earth. This is one of the reasons why, if we were to turn off carbon dioxide emissions today, the ocean would still be warming, since we're still warming the bottom of the ocean as it's transporting around and mixing. Of course, though, as we've seen, we will not be turning off carbon emissions anytime soon, apparently, collectively as the world. And sea ice is very reflective. So it's a nice image. You know, we have our sea ice in bright white and our ocean in dark blue. That darker ocean is absorbing much more heat and spreading it around to that circulation, whereas the sea ice is reflecting it and moderating the temperatures there. And then, you know, what I personally care about, of course, is the waves. Waves, these are the ones you're thinking about on the ocean, the ones you see at the beach. They are generated by wind blowing across the surface of the ocean. And you can see that with little ripples you get blowing into your tea when it's too hot, or your coffee, I guess. And those little ripples can grow if you keep putting in that wind energy and eventually become nice big waves, which are the ones we see at the ocean. So something like this. Our wind input is driving up that little ripples we can see towards in the middle there, and then they grow and grow to nice large waves as the wind blows. Now eventually the wind stops blowing and the waves actually reach some nice equilibrium out in the middle of the ocean, away from the coastline, and they become kind of well-developed waves. So this is our waves that we're now dealing with, and they're kind of nice and regular. And for all, you will of course be familiar with the real ocean being very much more chaotic. For the mathematicians in the audience, you know, these are our fundamental solutions of our partial differential equation that describe the actual oceans, but we can reconstruct the more complex oceans from these fundamental solutions, and we'll kind of see how that works a bit later. Okay, so our ocean has those waves, you know, they grew out from the wind and now they're just traveling. And there's kind of three ways that we describe these waves with numbers. So in particular, we have a length over which our waves repeat. This is the wavelength, so we can see that repetition here. My first chunk of the waves looks like the second one, and it just keeps repeating. And this distance over which it repeats is my wavelength. We also have the distance, the height of the waves. So that's given by the amplitude, and it measures the peak of the waves to the middle of our waves, which is 0, because I drew it nicely. And that's my amplitude. And then the third number, a bit more confusing in a static image, is the repetition in time. So if my waves go from left to right, then this chunk will replace this chunk, and it will actually look exactly the same as it did before. And the time over which that happens is the period. So you might, you could just follow this first, we'll just follow this wave. And it's kind of like there that it reaches a period. And that just keeps repeating. So that's the time over which it repeats. So those are the three numbers. And I haven't showed an equation in a while, so better do that. So to give a kind of overarching perspective, I can describe the water surface as the amplitude multiplied, and it is multiplied, by something that repeats every period in time, multiplied by something that repeats every wavelength in space. And just to complete that out, and you can kind of ignore this if you don't know any maths, but this is a full description here of these waves. Complex exponentials, sines, cosines. If you're familiar, then great. If you're not, that's okay. So what this is telling you is how those three numbers can change and what my different waves can look like. So I could change the amplitude and just make everything bigger. But I could also change the length over which those wave repeats, which just change the repetition in this over space. And I can change the period, the time over which it takes to repeat whatever wave is there. I will say that because of the nature of water and the particular waves that we're looking at, that wavelength and that period are actually intimately linked by the physics, and they give you a certain speed at which waves travel, which is why we're looking at just one wave. I'm not looking at all the different periods with every wavelength. We just have a single repetition in time matching that repetition in space due to the physics of the wave. Okay, that's waves. Now we want to look at sea ice. So sea ice floating out in the middle of the ocean. We have a nice big chunk, like, whoa, what is it? It's like 500 meters, but I guess it's a bit bigger. Okay, I didn't know I made it a bit funky. Anyway, it's about 500 meters long, 400, whoa. So we want to send waves into my sea ice cover. So I have that wave with that amplitude that I had before. I'm just going to send it into my sea ice cover. And the computer can solve this problem very easily. A lot of work has been done by my collaborators back at Adelaide on solving this problem. And indeed, you just get a nice video of waves interacting with the sea ice cover. And we'll go through this, but I guess the key things to note is here we can kind of see the poorness of the model in a lot of ways. So we have this weird thing going on here when the water wave meets the ice cover. We have some weird disconnect. That doesn't look very realistic. This is kind of the classic thing about mathematical modeling. All of our models are wrong, but some are very useful. And certainly we kind of have to accept these and learn about them and to develop our models, especially at the kind of scale that we'll need to look at the climate. But anyway, this is kind of the fun part, is playing with all the different models, but we're just going to look at one today. Okay, so my wave came in from the right, and what happened? Well, when it hits the sea ice cover, you get a bit of reflection back. Of course, if you've been in a bathtub, you push water, a wave will propagate, hit the edge, and come back. And now that's full reflection. What you get with sea ice cover is a partial reflection. So we don't get the full reflection back. And we can kind of see this reflected wave in this wave field to the left during that beat, while we're kind of getting that weird oscillation, modulation in the heights of the wave. It doesn't look, for instance, like this wave here at the end, which looks more like those waves I was showing you before. And to see that reflection, and in particular kind of understand how waves are combining in this model, we're going to look and break that down. So wave reflection, we had our incoming wave, which is that nice regular wave with a single amplitude, none of that weird beating effect going on. That hits my sea ice cover, and then we get a partial reflection, which is precisely this wave. Now, the weird thing about this, I guess, that's different, is it's actually traveling to the right instead of to the left. So it's coming back at us from the sea ice cover, and it's a much smaller amplitude, as we can see there. Now, how do these waves combine and give me back my actual solution that I had before? Well, it's actually just simple addition. And we can see that by looking at a particular point and kind of following the water surface at a point there. So I'm going to highlight this point here at 25 meters on the incoming wave, and it just travels along the surface. And we can see that number there is captured by the line length there. And likewise, for the reflected wave, we also have a point here in red, which travels up and down the wave, although we can see because the amplitude is smaller, it's a much smaller number. Okay, and now I'm going to show you the combined wave field in front of the sea ice cover and show you those two, the red dot plus the blue dot, which gives me a black dot, and we can see that here. So we can see that most of the wave movement is that incoming wave, which is that blue dashed line. And then we get a very little reflection, which is the red line. But that black line is just the red line plus the blue line. And of course, when it's negative, we kind of have to take away. But that's all handled just by adding a negative number. Okay, so that's what happens there with waves and reflections. And this is called linear superposition and is, again, a result kind of the underlying physics going on there. But it's kind of nice to know that waves just add on top of one another. Okay, so we can we've now got our wave being reflected and now also transmitted into the ice cover. So our wave gets into the ice cover, and the important things to note might be a bit hard to see, but there is a different wavelength. That length over which the wave repeats is a bit longer under the ice cover, and this is due to all the different properties of the ice. And the important things to know about ice is that it flexes and bends, it's elastic, and that elasticity is what contributes to the lengthening of the wave. The sea ice can only flex over a longer distance than it could under an unloaded surface if there was no ice cover there. So the elasticity lengthens the waves. We also have kind of counter force, but it's something shortening the wave, a counter effect, which is the mass loading. So we get added mass loaded onto that surface of the water. And that shortens the waves, but the elasticity dominates, meaning that we get that lengthening of the wave. And then the third important point about it is that we get all these physical phenomena that actually reduce wave energy as waves propagate under an ice cover. These are due to a number of effects, but we try and summarize them here as just a decay in amplitude. And so things like friction of the water surface with the ice cover and turbulence and all those kind of funky things that can happen in more complicated fluid interactions. Okay, so then my wave gets to the end of my ice cover and it actually reflects back as well. So I get a transmitted wave, it comes and hits the edge and it reflects back, which is why we might notice that very slight beating as well and modulation in the amplitudes out of that ice cover. So if you kind of look at this one, it kind of goes whoop, due to, again, that reflection effect. Well, that's a bit of a headache, right? Because now my reflected wave, it's going to come back. And it's going to bounce again off the front. And indeed, yes, that's what happens, and partially transmitted. And actually, yeah, it's very complicated, of course. That's only because I'm showing it as being kind of complicated in this description. Actually, the computer handles it very well, and there's a way to iteratively solve this without having to, keep track, look at all one wave, propagate, and then reflect it and do all that jazz. But you could do it that way, and why that kind of works, and you get a nice stable answer is each time it reflects, the amplitude decreases very significantly, and so you get a nice kind of limiting behavior for, again, all those mathematicians. But the computer handles it, and I get my one transmitted wave here after all that messy reflection back and forth between all the ice edges. And it's a very nice wave, it's one amplitude, one wavelength, one period, just propagating to the right. Okay, so that's sea ice and waves, problem solved. Does that look anything like the waves and the sea ice that we saw before? Well, no. In the previous examples, that ship going through the ocean, we had very small chunks of sea ice and very large waves. And the reason for that is that waves of significant amplitude, as they bend and flex the ice, can break the ice. And that's another process by which we lose wave energy. And in this case, my amplitudes were big enough to break the ice, and now I have 2 pieces of ice. Don't worry, the computer will handle it all, but of course, as you can imagine, it's very complicated. So I send my wave in, that's normal. Have a bit of reflection, and of course, not only do I get that reflection off the front, I get that transmitted wave, I get reflection back, I get a bit of transmission, I get a reflection back, I get a bit of transmission, and it's a bit of a complicated mess, but the computer solves it. Oh, yeah. And the computer solves it, and we'll just play it for that. There. And there you go. Yeah, so again, it still doesn't look very much like those waves, those big waves with very small chunks of sea ice. And indeed, these amplitudes are large enough to continue to break the ice. Yeah, well, that wasn't so hard, just 2 flows. Well, I'm going to, of course, ramp it up to get to something a bit more interesting. So this is, a huge number of, quite a few flows. My incoming wave, and the computer handles it very well, although it's looking a bit more funky. Certainly it's less obvious that the ice is bending and flexing, and it's more just kind of behaving as a rigid body, just kind of tilting in the wave and moving up and down. But we're kind of neglecting a surge, I guess, but that's okay. So, my waves continue to break the ice. And this is where the maths kind of comes into it. It's like, well, I can just keep breaking the ice. My computer can keep handling it. So I can start asking like weird questions like, well, I'll just keep breaking my ice and see what happens, So that's precisely what I did. It's really fine. You can maybe kind of make it out because the screen's big enough, but there are really small chunks of sea ice. And, I won't bore you with, all the little interactions and reflections, but they're all there in the computer code. And sure enough, it looks like a complete mess when you play it. Oh, huh. That looks like a relatively normal wave field. We don't see any individual effect of all those flows. In fact, it just looks like we have a single reflected wave back. We can kind of see that beating again. We have now kind of almost one transmitted wave. Now the wavelengths changed and the amplitudes changed between that original kind of solid piece of ice versus these very small chunks of sea ice. And we have a decay in amplitude. And for those who paid very close attention to that single piece of ice, you might have noticed that actually this is much more effective at reducing the wave amplitude over distance as well. So we can solve a very applied problem where we can start asking those curious questions, which spark your imagination. And actually this is now something that's much more like those waves that we were seeing in the ship video, where we have very large waves compared to very small chunks of sea ice. And so it's actually very applied, and it's solving an applied problem as well. I can really understand long waves in sea ice. And there's a couple more curious things that's happening as well. So I continued to break the ice and found that if you break the ice more, so if I took all those chunks of sea ice, cut them in half, sent my wave in again, I actually get the exact same waves that I saw in this video. So I have the same amplitude, have the same wavelength, and I can just keep breaking it. So there's some kind of limit to how far I can break my ice to it changing the waves that I get. So, that was surprising. The second thing that was actually very surprising, especially for my observationalists and experimentalist friends in sea ice community, is that this broken wave field is much more effective at dissipating wave energy. Now, based on those kind of multiple reflections, that might seem a bit obvious from this video, but it was definitely not obvious to the observationalists, because when they go out into the sea, they see kind of 2 main states. They see very solid ice with almost no waves in the ship, and then they see very broken ice with lots of waves. And so they were assuming that actually the broken ice was a much more dissipated wave energy, a lot less than the solid ice. But there's still some kind of discussions to be had around that. I'm not saying my model is correct at all, although it's instructive that such a thing exists. And I guess the more exciting thing from a mathematical perspective is that, okay, I solved the computer, it handled all the little bits of ice, it reflected all the waves and did all that fancy stuff. But I can actually solve this problem another way, the smarter way, which is I just have to look at a little chunk of sea ice and look at the reflection and transmission of that chunk, and I can determine what this wave field is, and that's what I did. So solving the periodic problem. And furthermore, waves in periodic media come up all the time. And that's really the power of mathematics, is that you see those profound connections between different applications. So I could now better understand what some of the acoustics, quantum mechanics, and optics people in wave science were talking about with their waves in periodic media, and a lot of the same fundamental maths there. Okay, so in summary, maths is profound play. That's what I view it as, and certainly I kind of see, I don't believe in toy models. All my models are toys. That's my view. We can solve very applied problems. I can tell you about, what waves in sea ice look like for my ship. But then, using the power of maths, I can actually understand a lot of different phenomena that actually have the same underlying behavior. And that's what's that profound nature of interacting with objects that I thought were a bit abstract and weird, points and lines, actually looking very normal to me. Like, for instance, acoustics problems compared to sea ice problems, and even electromagnetic problems as well. So yeah, thank you very much for listening.
Yeah, thank you so much for the talk. That was really, really amazing. So I thought it was interesting that all your models were sort of like one-dimensional waves. I was wondering, how good of a representation is that for reality when you have like sort of two-dimensional waves?
Yeah, I guess the main difference we can think about is in 2 dimensions, we have, of course, direction. So the waves don't just go back and forth, they go out in every direction. But, I mean, I haven't actually been able to investigate this fully, but I was in New Zealand last year, and when we look at the 2D model, we see a very similar kind of thing happen, actually, with very small plates and some kind of effective wave property that we see as well. So it might still hold in 2 dimensions and be very application driven. Yeah, and I guess what I should also say is that lots of the models previously were assuming that I had a continuous medium and matching the wavelength, the amplitude to what people observe. What this is able to do is take those fundamental physics and scale it up and see what that effective property should be based on those kind of more physical-based models. Yeah.
Thanks.
With climate change, is there going to be a decrease in sea ice? And if that is the case, what's the implication?
So yeah, we're running out of time to study sea ice before it disappears. Unfortunately, I think I saw one of the predictions that in this century, I think they were predicting an Arctic ice-free summer. That was a bit scary. Yeah, so we got to lose that reflectivity, which is kind of cooling, acting as a cooling for the Earth. We are going to have that kind of there's a potential, there's a lot of talk, and it's a bit hard because of the ocean dynamics, what's going on there, whether the circulations will continue or shut down. Not exactly across that. I guess something that's a bit scary as well is that sea ice actually acts as a barrier for waves reaching ice shelves. So we have our ice sheets in Antarctica. They are not sea ice, so sea ice was formed from the ocean surface freezing. Ice sheets are formed from snow being compacted over a very long time, and they're huge, they're very thick. There's stores of fresh water, and that's why the ocean surface is high compared to the last ice age, is because of those ice sheets taking up that water. Sea ice protects the ice sheets from the waves, and the waves actually cause disintegration and loss of the ice sheets, which can increase the speed at which they melt. And so, yeah, we might get increased sea level rise as well as a result.
Thank you again. Yeah, really cool. I was wondering, do you know like the maximum amplitude to like the maximum deformation a given size piece of ice can take from the amplitude of the wave before it breaks up?
Okay, yeah, I mean, honestly, no, but it depends a lot on the ice properties, and certainly you can figure out the elasticity of the ice, the mass of the ice, what the waves are, and find out what the critical strain should be based on a kind of simplified plastic elastic model, essentially. And people do that as well. Like I kind of showed, waves interacting with ice, but I didn't show the ice breaking, right? But people do study that as well.
When you're working on this model, or I guess any model, what process kind of goes into deciding what data, what variables you take into account into the model?
In one sense, we'd like to admit that we have thought about every model. I think you could definitely say there's probably some models that are favorites because of the history that's built up over them. In this particular one, this is kind of the minimum model that you might consider to have elasticity and added mass and waves. So kind of simplifying the model to really understand it is kind of the key aim there. But of course, we can then talk about more complicated waves. We could talk about nonlinear waves, for instance, as well, and have more complicated models. And the reason why I chose a much more simplified model is to get to those climate scales, you're going to need a quite simple model to describe that at the kind of ocean basin scale, like to talk about, the ocean around Antarctica. You need quite a simple model. So yeah, trying to pick something very simple that we understand better. And that's also, I guess, the joy of the maths is, a climate scientist's perspective would be just throw everything in there and try and make it work at the end. But that's not how we kind of see it. And a mathematician is like, let's pick a very simple model that we understand and say something a bit more deeply about it.
Thanks. Great talk. My question isn't really about maths so much, but would you like to just tell the audience a little bit about what you're doing in your role as Associate Dean and what you're trying to achieve in that for the university?
Yeah, so for all of our staff, we have a strategy in development, Indigenous strategy for the Faculty of Science. So we're going through consultations around that. And really the goal of the strategy and kind of what the portfolio, what the role oversees is everything Indigenous that the faculty touches, which is, everything. So obviously, or not obviously, but staff, increasing Indigenous, Aboriginal and Torres Strait Islander staff here at the Faculty of Science, increasing student numbers as well, making our staff and students more representative of the Australian public, indigenizing the curriculum, better replicating and I guess making sure that the way we talk about science is true to this place, and acknowledging kind of the history of that here, which is very deep and very old. And there's also a lot of benefits, I guess, to science as well for better acknowledging and understanding some of the knowledge that's held in community as well. And then research projects as well. So we have a number of research projects that are either about Indigenous knowledges or deal with Indigenous communities. And so trying to make sure that these are all done in the best way. And I guess the tricky thing about it is that we want all those pieces to move together, but we also want them to be interrelated, right? So we want our research project up in Narrabri, where we have a project on native grains, to deliver back to what we can talk about in the education space, or even maybe one day get students from that community to come here at the University of Sydney, learn and give back to their community as well. So all these things in a lot of different directions, but also working together in a harmonious way.
I know on the PowerPoint that you said the model said that the smaller pieces you cut the ice into, the better it dissipates the waves. So if that were true, would it be also an issue that they might just melt faster?
Yeah, so smaller ice melts faster. That's definitely true. So there's lots of thermodynamics that we're not taking into account. I guess what I'm probably more drawn to is talking about the waves there and kind of the underlying assumptions of the model. So the reason why we get increased dissipation or energy loss in our broken ice cover is because when we break the ice cover, the elasticity doesn't matter as much, and we get what's a more mass-loaded system. So we're just looking at the weight of the ice on our water be contributing. What this means is that we get a reduction in the wavelength. And when we reduce for the wavelength, we have, and we keep the same decay rate. Since the wavelength is smaller and the decay rate's the same, the waves decay much faster. So that's now, that is the assumption that the decay rate stays the same as you break the ice, which might not be true. And that could be one explanation for why the observations are a bit different than my model. But yes, there are lots of other effects that we're not taking into account. For instance, with broken ice melting faster, but also broken ice probably having some effect on the growth of sea ice. So you're talking about with melt, spring and summer, but we also have the growth of the sea ice in autumn and winter, and they probably have an effect on both. That would be interesting to look at.
So I thought it was interesting that you said that your model sort of contradicted the observations that the observationalists saw. I was wondering if you had any like guesses or hypotheses as to why that was the case.
Yeah, I mean, there's a couple things that could be going on. So yeah, what's probably not as obvious there that I didn't highlight was that in a solid piece of ice, you get a large reduction in the amplitude initially. You get a much larger reflection back than the very broken ice cover. So it could be that the change in the initial amplitude in the ice cover is the dominant force that they saw, and they didn't see that larger decrease in wave energy. That's the one that agrees with the model. But I guess, as I kind of pointed out too, it could be that the model doesn't apply. It's not the same dissipation model for that large chunk of ice as it is for the small chunk of ice, which is what I assume in the model. So yeah, those are the kind of the two main ones, I guess, that are front of mind.
In the like hypothetical occurrence of like the majority of the ice cover sort of dissipates or melts, would that mean like a large amount of the waves in the Arctic and Antarctic would get a lot larger? And if so, how would that sort of affect the ecosystem there?
Yeah, that's a really good point as well, and kind of goes to the ice sheets, right? So that sea ice protects not just the ice sheets, as I kind of mentioned, but also the coastline of the, particularly the Antarctic, although I guess there's also the coastlines of the Arctic, but they're at the edges, whereas the Antarctic coastline is in the middle. So you can kind of, the Antarctic one seems a bit more protective, whereas in the Arctic, it's already receded, I guess, from the coastline in summer. Yeah, so there's definitely, there's a recent study actually about the the propagation of plastics from Australia, from New Zealand, and from some of the subantarctic islands of plastics put in the ocean, and when do they reach the coastline? And this is going to be exacerbated under climate change, where we don't have sea ice protecting those coastlines. Yeah, and yeah, propagating species as well, I am sure. In fact, that's what they were interested in, is how organisms are going to propagate to the coastline.
Thank you very much for the talk. I have a question about when you break down the pieces of the smaller ices, whether the distance between each small pieces will impact on the reflection back to the wave?
Yeah, very good question. So I guess what you can think about is I've fixed the concentration of my ice cover. So I think in that one, it was a 95% ice concentration. So 95% of 100 to 600, I guess, was ice. And so that was a 5% of open water between all the ice cover. Now, if I decrease the concentration of ice, so it's just small chunks with bigger gaps of water, what happens is it looks more like open water. So I actually get an increase in wavelength since it's mainly mass loaded. That's probably not so interesting. What's probably more obvious is that the amplitude and the decay rate decreases as well. So it just looks more like open water. Like if I had a 0% concentration, then it's the open water, it just propagates endlessly, and there's this kind of nice transition between those two states. And actually the recent paper is very much looking at what happens, what the effect of concentration is.
Thanks everyone for the question and answers, and let's thank the speaker, Dr. Jordan Pitt, again for this very wonderful talk.